we defined the term called mean temperature difference, and we derived expressions for the mean temperature difference in parallel flow and in counter flow. You would recall that the logarithm of delta T I by delta T E occurs in the denominator of the expressions, both the expressions. For this reason, the mean temperature difference in a heat exchanger is also referred to as the logarithmic mean temperature difference, and the symbol capital LMTD, all letters in capital LMTD, is used instead of delta Tm by many authors and many writers. Then we moved on to discussing how to obtain the mean temperature difference in cross flow. Now, you will recall that what emerged after discussing the temperature profiles on the hot side of the hot side fluid and the cold side fluid was that in cross flow, unlike parallel flow or counter flow, the temperature is not a function of one variable, the temperature is a function of two variables x and y. If both fluids are unmixed, temperature T h is a function of x and y, temperature T c is a function of x and y. If both fluids are mixed, one fluid is a temperature of fluid's temperature is a function of x, the other fluid's temperature is a function of y. And if one is mixed and the other is unmixed, the unmixed is a function of x and y, whereas the mixed one is a function only of one variable. But regardless of whichever case it is, the fact is the temperatures on the two sides are not functions of one variable x, as is the case in counter flow or cross flow, but are a function of x and y. And therefore, in order to obtain the mean temperature difference, it becomes necessary to perform numerical integrations to obtain expressions for the mean temperature difference. And you will also recall that towards the end I said the mean temperature difference is given, the values are given in terms of a correction factor f, and f is defined as the mean temperature difference in cross flow divided by the mean temperature difference if the arrangement had been counter flow. This is where we stopped. So, let us take off from that again. We were getting results for the mean temperature difference in cross flow we were deriving results for this case, and towards the end we said f, we are going to express the results in the form of correction factor f, and f is equal to the delta T m which we are looking for, the delta T m in cross flow, this is the quantity we are looking for, divided by the delta T m if the arrangement had been counter flow, delta T m if the arrangement was counter flow. And we know how to calculate the denominator. And in case the fluid is unmixed on one side, remember you have to take the mean temperature of the fluid, the bulk mean temperature of the fluid leaving the heat exchanger, and substitute that in the expression for delta T m for obtaining the counter flow delta T m. Now, the results for given value, before I go to the actual presentation of the values of f, how they are presented, let me just make a statement. For given values of T h I, T h e, T c I and T c e, that is given values of the inlet and outlet temperatures on the hot side and cold side, for I am making a statement, for given values of T h I, T h e, T c I and T c e, the for given values, comma, the delta Tm in counterflow is the highest. That is, for given values of these 4 quantities, if I calculate delta Tm in parallel flow, if I calculate delta Tm in counter flow, in cross flow for any of the 3 cases, what I will find is the delta Tm in counter flow is the highest of all flow arrangements amongst all flow arrangements. This is what we will find. Therefore, it follows, since delta Tm in counterflow is always going to be the highest, it follows that F, the correction factor F, which we have defined above here, must be always in the range 0 to 1. It must be a number which will range between 0 and 1, 0 less than or equal to f less than or equal to 1, that follows. And with this definition of f, if we are to calculate the q for a cross flow arrangement, therefore, if we are to calculate q for a cross flow arrangement, we will get q for a cross flow arrangement is equal to u a delta Tm cross flow, which is with the definition of f equal to u a f delta Tm counter flow. So, when we have a cross flow problem, a situation of cross flow, we will calculate the delta Tm in counter flow, get f which has been obtained by numerical integration, then which I will tell you shortly how we get it from the various charts or graphs available, and substitute into this as our basic performance equation. Now, the quantity f, how do we get it? F based on the numerical integrations, f is plotted, the results which have been obtained by numerical integration, f is plotted as a function of 2 parameters. R and S, dimensionless parameters R and S. R is defined as, let me put down the definitions, R is equal to T1I minus T1E divided by T2E minus T2I, and I will tell you in a moment what is 1, what are the subscripts 1 and 2, and S is equal to T2E minus T2I divided by T1I minus T2I. Now, the subscripts 1 and 2 correspond to the 2 fluids. The subscripts 1 and 2 corresponds to the 2 fluids, correspond to the 2 fluids. Subscripts 1 and 2, 1 and 2 correspond to the 2 fluids. For cases 1 and 3, what are cases 1 and 3? Cases 1 and 3 is, case 1 is both fluids unmixed, and case 3 is both fluids mixed. For cases 1 and 3 of cross flow, these two cases of cross flow, it is immaterial which subscript corresponds to the hot side and which to the cold side. It does not matter, you can take either way, the results are valid. That means, for this situation, cases 1 and 3, these situations, for cases 1 and 3, for cases 1 and 3, subscript 1 can be equal to H and subscript 2 can be equal to C, or we may have the reverse, subscript 1 can be equal to C and subscript 2 can be equal to H. It does not matter which way you take it, both are equally acceptable, the results, numerical results come out right. It is only for case 2 that you have to be a little careful. For case 2, let me put down what you do. For case 2, that is one fluid mixed and the other unmixed, care has to be taken, care must be taken to see that the mixed fluid has subscript 1. The mixed fluid may be the hot fluid or the cold fluid, it does not matter which one, but take care to see that the mixed fluid is given subscript 1 and the unmixed fluid automatically becomes subscript 2. That is the only precaution we have to take. So, these are the two parameters in terms of which the values of f are found out. Now, what are these parameters? What is the dimensionless parameter R? If you look at it, it is nothing but the ratio of the change of temperatures, the ratio of the change of temperatures of the two fluids, that is what is R. And R by definition therefore, will be a positive quantity, but unbounded, greater than or equal to 0, in the limit 0. What is S? The parameter S, the second dimensionless quantity, it is the ratio of change in temperature of one of the fluids ratio of change of temperature of one of the fluids to the difference of inlet temperatures of the two fluids, THI minus TCI. That is what it is. So, automatically by definition you can see the parameter S is going to be a number which is going to be between 0 and 1. The particular results that we get for R, the results that we get for R, if you were to plot them, first just let me show the variation. It looks something like this. Suppose this is the the results that are obtained based on the numerical integration for any of the cases 1, 2, 3, if I plot f against s, s can range from 0 to 1, f can also range from 0 to 1, then for a particular value of r, a typical variation of s may be something like this. This is some particular value of r, some specified value of r. We will get, this is the kind of variation which we get for f, and these have been obtained based on the numerical integration which I mentioned to you earlier. Now, let us look at actual results which have been obtained. I am going to show you 3 charts for the 3 cases of cross flow. This is the chart which I am showing you now. The correction factor F for the mean temperature difference in single pass cross flow, both fluids unmixed. Case 1, what we have called. These are results based on the numerical integration to obtain the mean temperature difference in cross flow and to get the correction factor F. So, on the y axis you have the correction factor, on the x axis you have the parameter S, and the different values for the different graphs are the values of r, ranging here from 0.2 to 4. The value of r equal to 0 will be the horizontal line and the vertical line. This will correspond to r equal to 0. So, these are the results for the correction factor F for the case of both fluids unmixed. Now, let us look at the next results. I am just showing these results which are to be used for actual calculations. The next figure shows the let me read out, shows the correction factor F for mean temperature difference in single pass cross flow, fluid with subscript 1 mixed, fluid with subscript 2 unmixed. The nature of the curves is of course the same, keep that in mind, but the values are very different for the different cases. Again it is f plotted against s with r as the parameter varying from 0 on to 4. 0 is this case, the horizontal and the vertical line, that is 0, then 0.2, 0.4, 0.6, 0.8 all the way up to 4. These are typical values encountered in practice. R greater than 4 is probably not encountered very often. So, the values are not plotted there at all. And then finally, here is the correction factor F, results for correction factor F plotted for mean temperature difference in single pass cross flow for the case of both fluids mixed. Similar results, but of course, numerical values are different. So, depending upon which cross flow case you have, you will go to the appropriate figure and read off the values of F. That is the point I want to make. We will do a numerical example, so that you will be able to learn how to use these graphs. Now, let us just talk briefly about some special cases before we do some numerical examples. I am going to do a couple of numerical examples to illustrate all these ideas. First, let us just look at 2 special cases. These 2 special cases are the following: A, m dot h Cph tending to infinity. This is one special case. The value of the product of the flow rate and the specific heat on the hot side is very high, tending to infinity. Or automatically it follows that if Q is finite and m dot h Cph tends to infinity, that the change of temperature on the hot side of the hot side fluid must be tending to 0. B is the reverse case, the other case, that is m dot C Cpc tends to infinity. The product of the flow rate and the heat capacity on the cold side is tending to infinity, and therefore, since it is tending to infinity, Tce minus Tci is tending to 0. So, these are 2 special cases. Now, if you were to calculate the mean temperature difference for these 2 cases, that is either A or B, if you were to calculate the mean temperature difference for these 2 cases, what you will find is the value of the mean temperature difference will be the same, whether the arrangement is parallel flow, counter flow or cross flow, any of the cases of cross flow. You can do that yourself and convince yourself that that is what will happen. The fluid temperature on one side does not change, and as a result the values of mean temperature difference come out to be the same whatever be the flow arrangement. This I would like you to check it on your own, and in your mind you should be able to explain why this is also happening. Cases A and B, incidentally, one way of looking at them is to say that m dot h C P h is tending to infinity. The other way of looking at case A is to say it is a case in which a saturated vapor is condensing. Suppose I have a saturated vapor at some temperature T s, and it is condensing at the same temperature, obviously, since it is saturated vapor. The temperature will not change as it changes from vapor to liquid. So, automatically the temperature T s will not change on the hot side. So, case A also corresponds to a saturated vapor condensing, and vice versa case B corresponds to a saturated liquid evaporating. So, remember, case A and case B can be interpreted in two ways. One interpretation is the flow rates are very high on one or the other side. The other interpretation is that case A corresponds to the case of saturated vapor condensing and case B to a saturated liquid evaporating. So, these are two special cases, and as I said, it is worth noting that the mean temperature difference is the same in these cases regardless of the flow arrangement. Now, the same idea again I have shown in a sketch here. So, I will be sort of repeating things here. This is the figure A corresponding to m dot h C P h tending to infinity. The temperature on the hot side does not change, or this could be a fluid vapor condensing. The temperature on the cold side is increasing. All right. The B is the case of m dot C C P c tending to infinity. So, the temperature on the cold side does not change. This could be a saturated liquid evaporating, and the hot side fluid is giving up heat slowly like this. The way I have shown it, it is parallel flow, but remember, even if it is counter flow, all that will happen is I will get a mirror image kind of variation of T c in the other direction, and therefore, you can see why the mean temperature difference is the same whether it is counter flow, cross flow or parallel flow. So, these are the two special cases. Now, let us do a couple of problems to illustrate all these ideas of mean temperature difference for different flow arrangements. Let us take one example. A numerical example. We have a parallel flow heat exchanger to be designed, a parallel flow heat exchanger to be designed to cool 5 kilograms per second of air from 500 centigrade to 350 centigrade by an equal flow rate of air entering at 90 degrees centigrade. 5 kg per second of air to be cooled from 500 to 350. On the cooling side, the same flow rate of air entering TCI being 90 degrees centigrade. We are given that the heat transfer coefficient on the hot side HH is equal to 60 and on the cold side HC is equal to 30. These are the values of H. Calculate the area A of the heat exchanger That is the example to be solved. Take Cp, we will need the value of Cp. Take Cp of air on both sides to be 1020 joules per Kelvin per kilogram Kelvin. Take this value of Cp. So, design a parallel flow heat exchanger, that means find the area A of a parallel flow heat exchanger for given conditions. Let us just draw a sketch of what we have, what we are asked to do. This is a, let us say let me draw the sketch of the heat exchanger. Let us say this is our heat exchanger, this is the heat transfer surface. The fluid on the hot side, it is a parallel flow heat exchanger, m dot h equal to 5 kilograms per second. M dot C is given to be the same, 5 kilograms per second. THI, you are told the inlet temperature on the hot side equal to 500 centigrade. TCI equal to 90 degrees centigrade. THE given to be 350 centigrade. The value of HH, heat transfer coefficient on the hot side, is equal to 60 in the usual units, watts per meter squared Kelvin, and the value of HC on the cold side equal to 30 watts per meter squared Kelvin. So, find the area, these are the exit points. Find the area A of the heat exchanger if the configuration is parallel flow. We can sketch the temperature profiles. On the hot side going to be something like this, on the cold side it is going to be something like this. This is 500, this is 90, this is 350. Now, the flow rates on the hot side and the cold side are equal, and the Cp's are given to be equal. Therefore, it follows that the change of temperature on the hot side and the change of temperature on the cold side must be equal. So, the change of temperature on the hot side is 150. So, it follows that the change of temperature on the cold side must be also 150. So, TCE must be equal to 240, that follows. I do not have to even do any real calculation for that. So, delta Ti is equal to 410 and delta Te is equal to 110 degrees centigrade. These are the temperature profiles on the two sides. These are the values of delta Ti and delta Te. It is relatively a very simple problem. We have to remember, we have to substitute into the expression Q is equal to U A delta Tm. So, we need to get Q, we need to get U, we need to get delta Tm, then we will get the value of A. So, let us get them one by one. Let us get the value of first the value of Q. Q is equal to 1020, that is the specific heat into the flow rate 5 into the change of temperature on the hot side or cold side, does not matter which side you take, 500 minus 350, and that comes out to be 765 into 10 to the power of 3 watts. This is the heat transfer rate in the heat exchanger. The value of delta T m in parallel flow is equal to delta T I minus delta T E divided by log to the base e delta T I by delta T E. So, it is 410 minus 110 divided by logarithm to the base e 410 divided by 110, and that comes out to be 228.02 degrees centigrade. Now, we are given the values of H and H C. We are not told anything about fouling. So, we will have to make an assumption, first of all about fouling, and secondly about the thermal resistance B by K. We are not told anything about that. But notice the values of HH and HC are low. They are low because we have got air flowing as the heat transfer medium. So, values of HH and HC are bound to be of the order of 50, 60, 100, something like that, not going to be in thousands with air flows. Automatically, it follows that the thermal resistance of any metal wall, you can take any typical wall, a millimeter thick, 2 millimeters thick, take a conductivity of a metal of 10, 20, you will immediately see its thermal resistance will be insignificant compared to 1 upon HH or 1 upon HC. Similarly, if you look at any of the fouling factors that I have given you, you will remember those fouling factors are for situations involving liquids. With gases, fouling factors which are in the region of 0.301, 302, 304 in the usual units will be, their effect will be negligible compared to the thermal resistance offered because of the heat transfer coefficient. So, with gas flows, the values of neglecting fouling is a good assumption. Neglecting the thermal resistance of the metal wall, if that data is not available, is also a good assumption, and we can say in this situation 1 upon u is equal to 1 upon HH plus 1 upon HC. We will just leave out B by K, saying it is negligible, and we will also not consider fouling because it is bound to be negligible compared to the values of H that we are seeing for gas flows. So, all that we get is this is equal to 1 upon 60 plus 1 upon 30, and therefore, the value of u comes out to be equal to 20 watts per meter squared Kelvin. Now, substitute into our basic performance equation to get the value of A. So, our basic performance equation is Q is equal to U A delta T m, in this case delta T m in parallel flow. So, we will get A is equal to Q which is Q which is equal to 1020 into 5 into 150 divided by A U A, U is 20, sorry U delta T m. So, U is 20 and delta T m is 228.02. So, we get the area A of the heat exchanger to be 167.75 square meters. That is the answer to the problem, 167.75 square meters for the given data that we have got. Now, let us say instead of a parallel flow heat exchanger, the arrangement instead of being parallel flow is counter flow. I ask you calculate the area A of the heat exchanger if the flow arrangement is counter flow. Let us do a further calculation. Calculate the area of the heat exchanger if the flow arrangement is counterflow. In this case, notice we again have to substitute into the same expression q is equal to u a delta T m. Q is not going to change. Here is my basic expression, q is equal to u a delta T m. Q is not going to change, u is not going to change. What is going to change is the delta T m. So, get a new value of delta T m for counterflow situation and again substitute into our basic equation. So, what is delta T m in counterflow now? Let us calculate that. Delta T m in counterflow would be notice this is a case of counterflow with m dot h C P h equal to m dot c C P c. Notice that. Therefore, in this case with m dot h C P h equal to m dot c C P c, the temperature profiles on the two sides are going to be parallel lines like this. So, we are going to have 500 here hot side fluid entering temperature, 350 leaving, entering TCI 90, leaving TCE 240, and we will get the value of delta Ti and delta Te, both delta Ti and delta Te both in this case will be 260 degrees centigrade. So, delta Tm counterflow will be equal to the same. Delta Tm counterflow will also be equal to 260 degrees centigrade. This is the case of the two temperature profiles being parallel to each other. This is that special case which we talked of earlier. As I said, q and u do not change, therefore, A will be equal to the value of q, which is 765,000 watts, divided by the value of u and the value of delta Tm 260. So, we get 147.12 square meters. So, this is the value for the area A if the arrangement is counterflow. And I will make a statement here without proving it, that if it is a cross flow arrangement, any kind of cross flow arrangement, then you are going to get, since this is a counterflow arrangement is 147.12 and in parallel flow you have got 167.75, a cross flow arrangement, any cross flow arrangement would give an area between these two extremes. Parallel flow gives the highest, counterflow gives the least. You will get a value for cross flow in between these two. I am just making that as a statement. So, this is a good numerical example to illustrate how we substitute into our basic performance equation q is equal to u a delta Tm and calculate the area A of a heat exchanger for a given application. Now, let us do one more problem, another numerical example. The problem we are going to do now is the following. We say 1000 kilograms per hour of water at 50 degrees centigrade enters a single pass cross flow heat exchanger. And leaves at 40 degrees centigrade. A hot water stream 1000 kilograms per hour of water enters at 50, leaves at 40. The heat from this hot water, the heat is transferred to cooling water entering at 35 degrees centigrade and leaving at 40 degrees centigrade. The cooling water, which is cooling this hot water, enters at 35 and leaves at 40 degrees centigrade. Calculate the area of the heat exchanger if the fluids on both sides are unmixed. Take U to be 1000 watts per meter squared Kelvin with fouling included. That means, the effects of fouling are included in this value of U. Take the value of U to be 1000 watts per meter squared Kelvin and the value of Cp on both sides, the Cp for water on both sides to be 4174 joules per kilogram Kelvin. Take the value of Cp to be the following. It is a straightforward example of calculating area, very similar to the earlier one, excepting that now the flow configuration is cross flow with both fluids unmixed. Now, let us just draw a sketch. Here is, let us say, a schematic diagram. This is the area, the cross flow situation. Let us say this is the heat transfer area A, which we have to find out. This is the hot fluid entering here, m dot h equal to 1000 kg per hour, Thi entering at a temperature of 50 degrees centigrade, leaving at a temperature of hot fluid leaving at a temperature of 40 degrees centigrade. Cold fluid Tci entering with a temperature of 35 centigrade and leaving with a temperature of 40 degrees centigrade. Calculate the area A. Now, again our basic performance equation is Q is equal to U A delta T m. In this case, we are going to get the correction factor F. So, we will write this as U A F, which will come from the graphs, multiplied by delta T m if the arrangement had been counterflow. So, if I want to get the value of A, I should get Q, I should get U, I should get F. So, let us get each of the quantities. First of all, Q. What is Q equal to? Q is nothing but the flow rate on the hot side 1000 divided by 3600. So, many kilograms per second into 4174 is the value of Cp into the change of temperature on the hot side 50 minus 40, and that is equal to 11594.4 so many watts. So, that is the value of Q. What is delta T m in counterflow? Let us get the value of delta Tm in counter flow, delta Tm will be equal to, this is the, let us draw a sketch for a, as if it is a counter flow situation, starting with 50, going out at 40 on the hot side, cold side entering at 35 and leaving at 40. So, we have delta Ti is equal to 10 and delta Te equal to 5. So, we have 10 minus 5 divided by the logarithm 10 divided by 5, which comes out to be 7.21 degrees centigrade. And now, let us go to the charts. Since both fluids are unmixed, it is immaterial whether subscript 1 corresponds to the hot side and subscript 2 to the cold side, or vice versa. It does not matter which you take. So, we say take T1 equal to TH and T2 equal to TC. Let us take that. It does not matter which you take, you will get the same answers. Therefore, R is equal to THI minus THE divided by TCE minus TCI, which is equal to 50 minus 40 upon 40 minus 35, which is equal to 2, and S is equal to TCE minus TCI upon THI minus TCI, and that will be equal to 40 minus 35 divided by THI minus TCI, 50 minus 35, which is 0.333. Now, we go to the figure which I had shown you earlier for the case of the results obtained for single pass cross flow. Recall, I had given you some situations there, and if you recall, let us just show that figure again, both fluids unmixed. Here we have this is the situation, correction factor F for both fluids unmixed. Now, in this case, R is equal to 2 and S is equal to 0.333. So, this is the graph of R is equal to 2 here, this is the graph of R is equal to 2. Take S equal to 0.333, somewhere here, go up here to R is equal to 2, which means somewhere out here you will go at this point, then go horizontally and read off the value of F. You follow? So, here is the value of R equal to 2, get S equal to about 0.3, it will come somewhere here, go horizontally and you will get F is equal to 0.91 from the figure. F is equal to 0.91. Therefore, now last step, area A is equal to Q divided by U delta T m counter flow into F. So, it is equal to 11594.4 divided by the value of U is 1000, value of delta T m in counter flow is 7.21 and the value of F is 0.91. So, we get area A equal to 1.77 square meters, and that is the answer for this particular problem. That is the answer for this particular problem. So, now for different flow configurations, through the help of these two examples, we have illustrated how to obtain the area A for a given heat exchanger. Now, this is one technique, the Q, using the equation Q is equal to U A delta T M. This is one technique for finding out. The other technique which is also used, which is the other method which is also used for finding out the effect, area A of the heat exchanger or the performance of heat exchanger, is what is called as the effectiveness NTU method. And the effectiveness NTU method is, there are certain reasons why this particular method has been developed. So, next time we will look at the effectiveness NTU method, we will discuss it, derive some relations for it and show how it is also applied for doing calculations with heat exchangers.